So, good afternoon, everybody. I have a very tedious task today because after such a nice lunch, I am supposed to keep you focused on some theoretical stuff. So please accept my apologies from the very beginning. And I'm not going to talk about very complicated theoretical physics stuff. I'll try to be on the earth and, let's say, talk about more application. I don't have much experience with ink, and you guys, you are definitely more experienced and expert than myself. Therefore, I came here actually not to show you how cool we are, because we are, everybody is. I came here just to maybe get some answers to questions. So in the next few minutes, you will see what a theoretical physicist is doing with something he doesn't really have much clue about. And let's go ahead. Of course, I try to be as structured as possible. Therefore, like in school, I made up my own agenda. I try to stuck on the corporate design from IJC. So we have to be polite and make a short introduction. And I will tell you just some few words about my employee, about Heraeus. Afterwards, I decided to talk about some light sources, some bases, because you see them everywhere here in this exhibition hall. But I know for many companies, this is just a post-processing process, and nobody cares really how the ink is drying and how does it look like. And a particular topic, and maybe therefore I came here, is to learn a little bit more from you guys, from the manufacturer of ink, about these optical properties of the ink and the interaction between the ink and the wavelength, because this is what you need when you are trying to dry ink. Some new solutions I've seen as a possible solution for drying and get more optimal systems, and of course our lab systems where I've done all those trials I'm going to talk about in the next minutes. So, because I have to be polite and I still want to have my job, I want to say a few words about Heraeus. So Heraeus is actually a chemistry concern in Germany. It's a family-owned chemistry concern. And the main business from Heraeus is with precious metals. Additionally, there is another business from Heraeus working very well right now with quartz glass. So just to give you an example, quartz glass, yeah, we are doing a lot of work in optical fibers. So when you are using your mobile phones or your computers, also during the talks whatsoever, is because we are also working on this. So if the wireless works, it's because of us. If it doesn't work, it's because of the organization here. So actually what you are doing when you have precious metals, special metals, and also quartz glass, you are doing something like this. This is not my own invention. This comes from Edison. It's a lamp. It's an infrared lamp. So you see many of them here, exhibition, from Fresenius, from Ushio, from Heraeus, from Adfos. They are all over. And this is actually what you call, or what you need for the post-processing, for the drying processes in the printing. We are also doing those kind of lamps, and we are basically covering the entire spectra. You see here just a small overview. So we start from, let's say, nuclear decay, so from UV, very, very deep on the spectra, 172 nanometers, and we go up to the end of spectra, middle range or even far range spectra, up to 5,000 nanometer and even more. And one of those applications we have is, of course, drying and a solution, more or less, for printing and packaging. And this is why I'm here. So several applications of our lamps are either in UV region, so we try to cure with the UV ink. We also try to dry with the infrared, the water-based ink, and also some work on the, let's say, disinfection of surfaces and printed electronics. This is also one of our range. But I don't want to insist too much. let's have a look, first of all, but because we talk about post-processing in printing industry. We talk about drying. So, guys, you are doing ink, we are just doing lamps, and because I'm dealing a lot with customers, the customers are coming and asking for some lamps in order to dry ink, either water-based or UV ink and so on. And they expect from us a solution. So the first question I'm asking is, okay, what type of ink do you have? And if it's water-based ink, for example, how does it look like, the interaction between the ink and the wavelength? Do you know where your ink is absorbing, which wavelength is the right one? And of course, they don't know, because this is not their task and their issues. And therefore, what you can do when you have, let's say, such a bright spectra of products, you just try to understand, first of all, how your products are working, how the ink it behaves concerning your own process, and of course, you try to combine them together. So, the first topic, or the first, let's say, a small topic I want to talk about is the behavior of the infrared sources. So, as I mentioned before, you have basically in a lamp, it's standard, you have a quartz glass. Usually there is filled in with argon, or if you have halogen infrared region, there is a halogen circle inside. And of course this filament, which is usually out of tungsten. And okay, some additional reflectors and whatsoever. What is this? From the physical point of view, this is a kind of black body. And the black body has an emission. And the emission behaves like this. So basically the energy which is generated by this emitter has a more or less complicated form and depends on the wavelength and on the temperature. So if you have a black body, you are a black body, I'm a black body, the sun is a black body, for example. The sun is a perfect black body. You know, just as a small example, the sun has a temperature of 5,777 Kelvin, and it emits at a wavelength of 500 nanometer. The Earth, on the other hand, has a temperature of 290 Kelvin, and the emission wavelengths, for example, where the energy is maximum, is about 10 micrometers. And this is also a black body, in principle. And what you can see here on this very clearly diagram is how those sources behave like. So you see, for example, starting with higher temperature on this region, there are so-called halogen lamps. Usually they have a temperature roughly about 3000 Kelvin, more or less, and the emission is around 900 nanometer. When you decrease the temperature, of course you get on long wave region, and you also decrease the emitted energy. However, of course, the physics tells us everything about. However, what we have here, and therefore I wanted to show you this behavior of tungsten, for example, is not a perfect black body. And this is where the differences is coming from between different sources. So, a perfect body has the distribution I showed you before, but actually what we have here, it's a little bit different. So, what you see here, for example, is the emissivity of this filament. And this basically switches those sources from the black body. What you see here, for example, the emissivity depends, of course, on the wavelength and on the temperature. So, what is telling us when we get to, let's say, longer wavelength, there is not much to have from such an emitter. So it may be necessary to look for other materials or also for other emitters. From the physical point of view, this is the way we basically calculate the entire energy coming out from a source. So basically, there is a black body, and this black body is fitted to the optical properties of the material which is inside of one emitter. Just to give you a more clear example, and I'm talking about this emitter in particular because you find this emitter everywhere, is with tungsten inside. What you see here with the long lines is the behavior of a black body at a certain temperature. So it's basically the Planck law and the distribution of the spectral emission. What you see here actually with dashed line is what this such type of emitter can do. So there is always a deviation from such emitter from a standard black body. And this deviation, of course, can be calculated. It's called, I have to apologize, I forgot to put a T here. So I'm doing mea culpa. But let's get back to physics. You see basically the difference between a black body and such an emitter. Even more, there is a displacement in the emitting wavelength. So, as I mentioned before, such a black body is a basically emitting body with a certain temperature, and it emits on a given wavelength range. For the infrared, we talk about a continuum spectra because it actually has to do with a, let's say, movement of molecules inside of the black body. Therefore, you also have this continuous distribution. However, we need a reference for those emitters. Therefore, I told you all this story about black body. And what you see here is, for example, the behavior of such a lamp, let's say the red one, related to such a black body. Wien displacement laws, it's basically telling us where the maximum emission for which wavelength, the maximum emission of a certain temperature occurs. Therefore, it is so important. Additionally, knowing this, you also can know which is the right range, and for example, the region you can more or less fit to the optical properties of an ink if you know them. Therefore, I don't want to specify all those details, but what I was busy with in the last time is just to see the behavior and to compare, let's say, our simple lamps with a black body, and to have more or less the background of, let's say, optical behavior. So, we know a lot about lamps because this is our business, so we have to know them. We saw how they look like, how they behave like, where to emit. But now what's going on when we try to dry the ink with those lamps? And of course, in order to have an optimized interaction between two systems, you have to fit there. So concerning ink, if I would know where the ink absorbs, I can also answer the question, which is the right wavelength for this process? In order to do this, of course, I need to have a look at the optical properties of the inks. So we are doing with several inks and with the ink from our customers a lot of measurements. Unfortunately, I cannot show them. There are some realities issues. But I found this paper. This is actually from RICO. And you can see very clear how it's going on. So all other measurements we've done, this is basically pigment, and for water-based ink, show more or less the same behavior. I even asked yesterday some manufacturer, and they more or less confirmed me the same behavior of the ink. So, what do we have actually here? We have the absorption range of the black pigment, and we have the absorption range of the other, magenta, cyan, and yellow. We see basically in the shortwave, near infrared and shortwave region, which is the one over here, a very unstable behavior and the gap difference. So, of course, it will be perfect to fit my black body or my wavelength in this region, which is basically 850, 900 nanometer. But what about this region here? Why not to try on this region? So, what we have done so far, we basically try to focus on this region. We even try to move a little bit towards this region. So we change basically the tungsten with carbon. Tungsten has a very bad emission behavior. Carbon, for example, is a black body. So we talk about emission of roughly about 0.95. However, we are still on this region. What does it mean, this behavior? This behavior means that when you try to dry black and yellow ink, you will have different heating rate. And I think everybody knows this. And of course, you will have different also drying behavior. There are different methods to overcome this issue. Either in the printing machine, you build up different units, and you start with yellow, and end up with black. So yellow sees more or less more infrared units. Or you try to combine, let's say, radiation and convection. All those situations or all those solutions, sometimes they are time-consuming, energy-consuming, space-consuming. So it would be very nice to find something on this region. If we forget about pigment, the picture I just showed you before, and if we look at the water, because we talk about water-based ink, we see also that water has different absorption region. So there are all those known absorption region, 1400 nanometer, 1800 nanometer, but there is also here in this region, which is roughly about 3000 nanometer. Why not also to use this region? Therefore, and this is just the behavior of the emission spectra of different lamps to show you actually where we are right now and where I would like to be. So I would like to be here at 3000 nanometer because you have seen the ink is very nice here and the water is also very friendly on this region. And of course, we didn't have so far many chances. You see, for example, the black curve is the tungsten one, and this is pretty far away from 3000 nanometer. The carbon, which is more or less a black body, is also not close. And of course, when you do all those theoretical stuff, you need also some experimental proofs for this. So what I have done in order to see how the ink really behaves at different wavelength, in different wavelength region, I measure it. And this is actually what we are doing when we have such an application. So the customer is coming, brings its own ink, and wants to have a solution. And the solution may be a certain emitter, a hybrid system, whatsoever, but which one is the right one? So in order to be able to answer this question, we perform a lot of measurements of getting the heating rate of different type of inks under different wavelengths. So what you see here, for example, is the drying of a water-based ink, in this case with 95% water. This is actually for thermal printing heads. And on a very thin paper, uncoated paper with 90 grams per square meter, we measure the heating rate. It's a very simple setup in our lab. We have a system where we put different wavelength emitter inside. And of course, the energy density, we've done the measurements with different energy density. So just pay attention a little bit to the temperature, namely to the wavelength. The measurements were done with the wavelength from near infrared, so 2500 Celsius means roughly about 2800, 900 Kelvin. And afterwards, we move towards longer wavelengths, 2000, 2200. This is more or less the short range. And 1900, this is, goes to middle range. And you see the heating rate, or the drying rate, if you want, of this type of ink. So you see for this ink, for this type of ink, but just don't take it as a general solution. This is the right wavelength to dry it out. It's not near infrared, it's not carbon in this case, a black body. it's just this one, which is more or less close to short infrared. I also changed the energy density. Usually in printing or in the drawing, our drawing customers or printing machine manufacturer, they ask energy density about 100, 120 kilowatt per square meter. I just change it to see if there is the same behavior. And we see basically more or less the same behavior. This wavelength is the right one for this ink. So this is how we more or less primitively try to fit the ink with the wavelength. And therefore, we try to set up in our lab everything in order to do those measurements and to change basically very easily the wavelength. And this is just a setup of the new lab and of the new, let's say, solution we have to do this. You know, as a scientist, when you look for this behavior of the ink, and I mentioned you the 3000, basically the 3000 nanometer, and the differences you see between yellow and black. You do measurements again. So what I've done here are different measurements of yellow and black ink with 80% water inside, and with a near infrared emitter, with a middle wave emitter for different energy density. And what you can see here basically is more or less this difference in the heating rate of both. Therefore, we decided to get to the lab and try to build up our own black body. And how we did this, basically we combine more or less printing electronics and quartz glass technique. And I've taken a black body, which is a perfect black body, like you see over here. I put a reflector on top of it, and of course I need to bring energy inside. Therefore, I took the other idea from the printed electronics, where the guys, they want to have a very high conductivity. Actually, I don't want to have high conductivity, I want to have high resistance in order to heat up this piece of quartz glass. And I've done a kind of lamp, a kind of emitter, which is actually in the region of 3000 nanometer. And with this new emitter, I try to, let's say, more or less dry the black and the yellow ink. So what you see here basically is the heating rate of the black and yellow ink with a high energy emitter, which is basically a black body, 3000 nanometer, 700 centigrade temperature. On this region, there is more or less the heating rate. You see how the temperature in the ink behaves like with time. And this is just a different representation. So with this emitter, we manage more or less to get on the same level the black and the yellow ink. Of course, you can have a look. This is just a black body. It's not something unusual. Of course, it's just one example. I try to do this with different type of inks. So 80% water-based ink, 85% water-based ink, and so on. And there is always the same behavior. Yellow and black does not change. They don't react differently, because actually we are on this region, or 3000 nanometer, 700 degrees, and a very high energy density. And with this more or less new lamp, we are able to see no difference on the drying of different type of inks. So it's more or less a macroscopical approaches. Of course, we are trying to get more inside and do some simulation and so on. But what I want you to take with you is just looking at the optical behavior of the ink. You can find out the right lamp in order to dry it out. And also in order to avoid all of those differences between black and yellow. Those measurements were done in our lab, of course. We have already more or less our own lab system with this type of emitters inside. And there are here just some technical specification. Of course, we get very deep inside, we do some simulation, and we optimize them. However, I think this is not really the topic of my talk from today. What I want you to take with you is exactly this behavior. So ink and wavelength, they have to be fit together. There is no general solution for drying out a type of ink. You just have to try out different wavelength, different different systems, and yeah, get the best solution out of it. So thank you very much. Sorry, I think I passed away my time. Yes.